Hello everyone, this is Ketish here. In this video, I'm going to go through the AQA Combined Science Physics Paper 1 Foundation tier. This video is a full paper walkthrough. Now this paper is 1 hour 15 minutes long and it's out of 70 questions, 70 marks. And it has 6 questions. Now in this video, I will only be going through question 1 to 4. These are the foundation level questions. Question 5 is actually a higher level question. This question appears as question 1 in the higher tier, and question number 6 appears as question 2 in the higher tier. And I have done videos separately for these 2 questions, so I will link those videos at the end of this video. Let's have a look at question number 1, which is on the topic of particle model of matter. A student investigated the density of different types of rock. Now, working out the density practical is actually a required practical. Figure 1 shows a piece of limestone. The student was not able to calculate the volume of the piece of limestone using measurements taken with a ruler. Suggest what is the reason. Now the ruler is not very accurate. Now you can actually work out the volume. Remember from your maths, volume equals length times width times the height. Now if you had a regular shaped structure like this, or a cube, and you could work out the length, width and the height. Now this limestone is not a regular piece of structure or object. The piece of limestone has an irregular shape. Irregular is when you can't measure the length, width and the height using a ruler. Figure 2 shows some of the equipment given to the student. A limestone, a displacement can, also known as a Eureka can, measuring cylinders. They've given 2. You would actually use either one of them, and a beaker. Describe a method the student could use to determine the volume of the piece of limestone. How would you work out the volume of the limestone using this equipment? First of all, you'll take the displacement can and you will fill it with water. Now you can use either the large measuring cylinder or the beaker to fill it up with water. Now when you pour it with water, the water will actually reach up to this point. Now this bit is the spout and it'll start pouring out. So you can never add more water than this level anyway. So once you fill it up with water, then, so that's your first step, you place the limestone inside slowly, and you want to make sure that the entire limestone is at the bottom. You say it's fully submerged in the water. Now before you do that, you would want to place this third measuring cylinder at the bottom over here, so that any water that comes out when you put the rock inside, make sure you don't splash any water outside. The water level rises up and the water comes out and it fills into the measuring cylinder, and you can read out the volume from the measuring cylinder. That's how you would do it. So how do you write the answer for this? Here's the model answer. Add water to the displacement can until level with the spout. Place the limestone in the water. Avoid splashing water out of the displacement can. Collect the displaced water in the measuring cylinder. Measure the volume of the displaced water in the measuring cylinder, which will be equal to the volume of the limestone. The mass of the piece of limestone was 155 grams. The mass is 155. The volume of the piece of limestone is 62 centimeter cube. Calculate the density. So density, they have given you the equation. So mass is 155 divided by the volume is 62. That would give you an answer of 2.5 gram per centimeter cube. Question 1.4. Density can be measured in grams per centimeter cube. What is another unit for density? Now, instead of grams, you can use kilograms. Instead of centimeter cube, you can use meter cube. So that would be kilogram per meter cube. Figure 3 gives the density of some other types of rocks. So you have basalt. The type of rock is on the x-axis. Basalt density in gram per centimeter cube is given in the y-axis. So basalt is actually 3. If you look at the scale, 0.5 goes up after 5 boxes. So each box is 0.1. So this is granite is 2.25. Obsidian is 2.4. Oh, this won't be 2.25. It will be 2.75. Let me change that. 0.75. And pumice is 0.25. The student had a sample of an unknown type of rock. The density of this rock was 2.5 or 2.4 gram per centimeter cube. Draw a bar on the figure 3 to show the density of the unknown type of rock. So you already have this space at the end. So you want to make sure that the bar that you draw is actually the same width, right? That's 8 boxes here. So I would start here, and that would be the width of this box. This will be the unknown, and 2.4 is the same as obsidian. So I would start here to there. Let's draw the top line, and then you're slightly off, it's fine, but you want to make sure that is roughly the same as the others. Choose the sentence. The data in rock 3 suggests that the unknown type of rock is obsidian because it's the same height. The student cannot be certain that the unknown type of rock is one of the types of rock in figure 3. No. The student cannot be certain that the unknown type of rock is one of the types of rock in figure 3. Give a reason why. Now, based on the information in the graph, we think it's obsidian. But what if there are other types of rock with the same density? So, other types of rocks may have the same density as obsidian. Pumice is a type of rock that has holes in it. The holes contain air. Tick one box to show which diagram shows the arrangement of particles in air. Now, in air, they're separate or further away from each other, but they're not in regular arrangement, so it has to be this. This is actually the solid, and that's liquid, and this is gas. Complete the sentence. The holes containing air causes the density of pumice to be less than. Because remember, density depends on mass and volume. Having air means that it will have more volume, less than the density of other types of rocks. Yes. Let's have a look at question number 2, which is on the topic of energy. In a sport called far leaping, an athlete uses a long pole to cross a river. Figure 4 shows an athlete far leaping. So you have the athlete holding on to the pole. Okay. Figure 5 shows an athlete in 5 different stages of far leaping. So A is stationary, and B, they're running, and C is in the middle. That's the maximum height they actually reaching. Okay. And D, they have landed. So they're basically going in this path, which is called like a projectile motion. Complete the sentence. Choose the answers from the box. Between positions A and B, the athlete speeds up. There is an increase in the athlete's kinetic energy and a decrease in the athlete's, that would be chemical energy. Store of energy because they're using the energy in their muscles. Between positions C and D, B and C, the athlete jumps to the pole and climbs up it. Which statement describes a change in the athlete's energy between B and C? Elastic potential energy decreases. Nothing to do with elastic potential. Gravitational potential energy doesn't actually decrease because it increases because they're actually climbing up the pole. Now, question 2.3. The pole falls from position C. The athlete lets go of the pole and lands on position D. The change in height of the athlete between positions C and D. Remember, the athlete was going in that shape. C was here and D falls from position C. Let's have a look at it again. Yes. So yeah, C is in the middle. So C is over there, D is over here. The change in height of the athlete, position C and D, is 3 meters. Okay, that's 3 meters. Mass of the athlete is 50. Gravitational field strength is 9.8. Calculate the change in gravitational potential energy of the athlete between C and D. They have already given us the equation. So the mass is 50 multiplied by 9.8 multiplied by the change in height, which is 3. That would give you 1470 joules. 70. The kinetic energy of the athlete in position D is 1600 joules. Mass of athlete is 50. Calculate the speed of the athlete at position D. Now the speed is given by this equation. Speed equals the square root of 2 multiplied by the kinetic energy divided by the mass. Choose the unit from the box. Now, let's work out the speed first. Speed equals the square root of 2 multiplied by the kinetic energy, which is 1600. 1600 divided by the mass was 50, if I remember correctly. Yes, and that would give me an answer of 8. So the speed is 8. Now speed is measured in meters per second. Figure 5 is repeated below. At positions A and E, the athlete is standing still. Why does the athlete have less energy in position E than in A? Now, although they are standing, why does the athlete have less energy in position E? Now, position E is actually slightly higher than position A. So they should actually have more energy than A. But they're saying the athlete has less energy. Why would that be? Because energy has been transferred from the athlete to the air. which would have happened because the athlete, while they were running and doing this entire activity, their body could have actually got warm, which eventually cools down. So the energy inside the body has actually transferred thermal energy and into the air, right? The air temperature has decreased. Now the height of the athlete above the water has increased. That would actually increase the energy, not decrease it. Athletes have a large power output when they are far leaping. What is meant by the power of an athlete? Power, if you don't know the definition, power, if you look at the equation sheet, is equal to the energy transfer divided by the time. So the rate at which athletes transfer energy, that is correct. It's not the maximum force, nothing to do with the force. It's not the total energy transferred. The total energy transferred generally remains the same. A second athlete crossed the same river by far leaping. The second athlete has less power than the first athlete when running between positions A and B. Complete the sentence, choose the answers. Each answer may be used once, more than once, or not at all. Two factors that could explain why the second athlete has less power than the first athlete were: the time taken for the second athlete to run between position A and B was, remember again, power is energy divided by the time. If you increase the time, that means the power is going to go down. So the time taken for the second athlete to run between positions A and B was more than. The work done by the second athlete was, that should be less than, because if they do more work, that means they're transferring more energy. So that should be less than. That brings us to the end of question number 2. Let's have a look at question number 3, which is on the topic of electricity. A filament lamp breaks if the electric current in the lamp becomes too big. What is the correct symbol for the filament lamp? That should be the middle one. This one is an LED, a light emitting diode. This is the diode bit which is inside the circle, and these two arrows indicate the light is actually given out. Now this is a LDR, light dependent resistor. This rectangular shape inside the circle is representing a resistor, and there is light hitting that with the arrow coming in. What is meant by an electric current? Current, the energy carried by each unit of charge. Now that would be incorrect. The flow of electrical charge is actually the current. And manufacturer investigated the maximum current value for some filament lamps. Figure 6 shows the symbols for an ammeter, a battery, and a variable resistor. The manufacturer connected an ammeter, battery, filament lamp, and variable resistor in series. Draw a circuit diagram to show the manufacturer's circuit. Include the symbol for a filament lamp from question 3.1. So it's only 1 mark. So let's start off with the battery. To the battery, I'm going to connect the ammeter to the ammeter. So I've connected the battery and the ammeter. I'm going to connect the filament lamp, and to that the variable resistor. Again, I'm using the symbols that is already given here. So the variable resistor, what could the manufacturer, how could the manufacturer increase the current in the filament lamp? Well, to increase the current in the filament lamp, they need to adjust the variable resistor. Add an extra ammeter will not help. Decrease the resistance in the variable resistor. Use a battery with a smaller potential difference will not help. It is number 2. When the potential difference across the lamp was 0.75 volts and the current in the filament lamp is 0.16 amps, calculate the power. Power is potential difference, which is 0.75 multiplied by the current, which is 0.16. That is equal to 0.12. 0.12. Write down the equation which links charge flow Q, current I, and time t. If you look in the equation sheet, you will find Q equals IT. Charge is equal to the current multiplied by the time. You can write the symbol equation or the word equation. The manufacturer increased the current in the filament lamp to 200 milliamps. So this lowercase m is standing for milliamps. Calculate the charge flow through the lamp in 15 seconds. So that's my time. Now in order to do that, I need to use this equation. Q equals IT. Now time is given in milliseconds. I need to convert that to amps. For that, I will have to divide that by 1000. That gives me 0.2 amps. So putting that into the equation, this is why they're giving you 3 marks. So this gives you a mark for the conversion. If you fail to do that, you lose a mark. So the current is 0.2 multiplied by 15. That gives you 3 coulombs. The manufacturer increased the current of the filament lamp from 200 milliamps. The filament in the lamp broke when the current reached 320 milliamps. How many times greater than 200 milliamps was the current at which the filament broke? Now, if I divide 320 divided by 200, it will give me 1.6. So it's 1.6 times. The manufacturer tested lots of filament lamps. The current at which the filament lamps broke was 320 plus or minus 60 milliamps. So it could range. It's not always breaking at 320. It could be 360 plus 80. That brings to 380. Or it could be 60 less, which means there is 240. So what is the range of currents at which the filament lamp broke? So 320 plus 60. If I write minus 60 on this side, minus 60. Now that would give me 240 volts and 380 volts. So I got it right. No, not 40. It'll be 260. Right, 260 to 380. That's the last one. That brings us to the end of question number 3. Let's have a look at question number 4, which is on the topic of energy. Solar intensity is a measure of the radiation received from the sun at the surface of the earth. Figure 7 shows how the mean solar intensity changes with the distance from the equator. So in this line graph, the distance from the equator in kilometers is starting at 0 and it's going up to 10,000. You can see that the mean solar intensity is starting there. It's actually going down, not steadily because it's not a straight line. It's a curve, at least for part of it. Towards the end, it's actually this between 6,000 to 10,000. It actually looks like a straight line. So let me redraw that. See if I can draw a straight line through this. Yeah, so at least from 7,000 to 10,000 it's actually a straight line, otherwise it's actually going down. Right, so let's have a look at the question. The city of Athens is 4,200 kilometers. Let me use a different color. From the equator, what is the mean solar intensity in Athens? So from 0 to 2000, that's 10 boxes. So if I divide 2000 by 10, I would get 200. So 4,200 is actually going to be at this point. So one box that is right up there, which is at 300. So the answer is 300 watts per meter squared. Solar water heaters use radiation from the sun to heat water. The heated water is stored in a water tank. Figure 8 shows a solar water heater on the roof of a building. You have the water tank and the solar heating panels. Cities closer to the equator have many more buildings with solar water heaters than cities further away from the heater. Suggest why. Okay, cities closer to the equator. Now, closer to the equator means that you're receiving more sunlight, obviously, than cities further away from the equator, because the solar intensity, remember, if it's near the equator, then you're getting a higher solar intensity than if you're further away. So cities closer to the equator receive a greater solar intensity. The use of solar water heaters may reduce the need to burn fossil fuels. Complete the sentence. Burning fossil fuels contributes to global warming because there's an increase in the amount of carbon dioxide in the atmosphere. The efficiency of the solar water heater is 0.61. Calculate the useful power output when the total power input to the solar water heater is 1100 watts. Use the equation useful power output is equal to the efficiency, which is 0.61 multiplied by the total power input, which is 1100. That gives me 671 watts. 671. Different solar water heaters have different sized heating panels. Suggest how the size of the heating panels affect the input power to a solar water heater. Now, if you have bigger heating panels, that means you're going to catch more sunlight. That means it has a bigger input power. So larger heating panels have a greater input power. Water has high specific heat capacity. What is meant by the specific heat capacity of water? Now, this is a definition that you will need to know, which is linked to a required practical on specific heat capacity. So the amount of energy, the energy required to change the state, it's not to do with the state, that is specific latent heat. So that can't be it. You don't have to put a cross. I'm just putting a cross just to tick it off. the energy required to increase the temperature. Yes, increase the temperature of 1 kilogram of water, 1 by degree Celsius. That is correct. Let's get rid of this to avoid any confusion. It is nothing to do with the power as well. The water tank contained 80 kilograms of water. The change in thermal energy of the water was 8,400,000 joules. Specific heat capacity of water is 4,200. Calculate the temperature change of the water. You have to use the physics equation sheet and you will find this equation. Energy transferred equals the mass multiplied by the specific heat capacity multiplied by the temperature change, which is delta theta. So 8,400,000 equals the mass is 80 multiplied by the specific heat capacity multiplied by the, oops, they have actually given us the specific heat capacity. So which is 4,200 multiplied by the temperature change delta theta. Rearranging the equation, delta theta is equal to 8,400,000 divided by 80 times 4,200. That gives me 25 degrees Celsius. The water tank is thermally insulated. How does the thermal insulation affect the rate of energy transfer from the water in the tank? Now, if it's thermally insulated, that means it's wrapped up, it's not losing a lot of heat, so does not lose heat. That's why it's insulated means. How does the thermal insulation affect the rate of energy transfer? Well, it's not going to increase the rate, it's going to reduce it. Thermal insulation decreases the rate of energy transfer. Table 1 shows information about different materials. You've got materials A, B, C, and D. Thermal conductivity is 3, 2, 8, and 4. Which material in table 1 is the best thermal insulator? Now, if thermal conductivity is bigger, it's a good conductor. Two is poor conductor. That means B is the insulator. That brings us to the end of question number 4. Now, question number 5, like I said, is appearing as question 1 in the higher paper, which is on the topic of electricity, and it's out of 11 marks. And question number 6 appears as question 2 in the higher paper, which is on the topic of atomic structure. So I will link videos for those 2 questions separately at the end of this video. Please check those out. Thanks for watching, and I will see you in the next paper.